Okay, in this video, we're going to talk about section 4.2 dealing with second derivatives and graphs. And in this video, we're going to find second derivatives of functions, also going to find inflection points. Then we're going to identify intervals of graphs of functions with certain properties and determine inflection points. And then we're going to be solving application problems that involve the graph of a function's second derivative. All right, so in the last video, section 4.1, we were dealing with the first derivative, which was helping us to determine the intervals where the function would be increasing and decreasing, and also that also told us what our critical numbers are. All right, so in second derivatives, when we deal with second derivatives, we're going to be looking for something called concavity. So let me introduce to you this term, concavity. The terms concave up or simply concave upward, that's used to describe a portion of the graph that opens upward. So let's say I had a graph that looks like this. So concave up is just a portion of this graph that opens upward as you see here. Concave downward, or concave down simply, would be used to describe a portion of the graph that opens downward. So in this graph, this part right here represents the portion of the graph that's concave down. Okay. Now another way you can look at concavity would be something like this. If you have any secant connecting 2 points on the graph, and that on that interval it lies above the graph, then we can say that the graph is concave up. So something that's concave up would look like this. See right here, there's the secant line here, and I'll outline that in color. That secant line, of course, is just a line that connects 2 points on the graph. That would be concave up, because notice that the secant line is above the graph. Now, if the secant line is below the graph, on the other hand, then that means the graph would be concave down on that interval. So here, this line that I'm going to outline in red, as you can see here, that line is concave. That means the line is below the graph, meaning from this interval, the graph is concave down. Okay? So that's what concavity is. It could be concave up or concave down. All right, on the next page is a concavity test. The graph of the function f is concave up on the interval AB, and that's the open interval AB, if f prime of x is increasing on the open interval a comma b, and is concave down on the interval AB, if f prime of x is decreasing on that open interval AB. All right, now before we go into more detail about our concavity test, we have to know what the second derivative is, okay? Because when we use what they call the second derivative test, we're going to have to determine whether it's going to be concave up or down, and we have to take its second derivative. So here's a notation. For y equal f of x, the second derivative of f, provided if it exists, is the derivative of the first derivative. Okay? And the notation would be this: y double prime equaling to f double prime of x, and that's equaling to the second derivative of the function f of x with respect to x. Okay? So in order to find the second derivative, you must find the first derivative, because it's that first derivative is what's going to help you identify the second derivative. And here's some examples of just that. Starting with this first example, let's say we got f of x is equal to 5x to the fourth minus 8x squared plus 3x minus 9. And I want to find the second derivative of the function f of x. Okay? So let's find what f prime of x is going to be. That's the first derivative. So f prime of x is this. We bring the exponent down, multiply by 5, that will be 20. So it'll be 20. Copy the x over to the 1 less power, so it'll be 20x cubed minus. Bring 2 down, multiplied by 8, it'll be 16, so it'll be minus 16. Copy the x down to the 1 less power. The derivative of 3x is 3. And the derivative of minus 9 is 0. So f prime of x is 20x cubed minus 16x plus 3. Now, let's find the second derivative. Since we know what the first derivative is, we're going to find its second derivative, which is f double prime of x. So here, to find that second derivative, here's the first derivative. We bring the 3 down, multiply by 20, that will be 60. Copy the x down to the 1 less power, so it'll be 60x squared. The derivative of minus 16x will be a minus 16. So f double prime of x will be 60x squared minus 16. All right, here's another example. Let's say we had something like this. We want to find h double prime of x, where h of x is equal to 9x to the negative 4 minus 5x to the negative 8 power. So here's h of x. So let's find out what h prime of x is. That's the first derivative. All right, so here we use the power rule on each term by bringing the exponent in front and multiplying it by that coefficient. So if I do negative 4 times the 9 in front, that'd be negative 36. Copy the x over to the 1 less power, so negative 4 minus 1 would be negative 5. And then bring the minus 8 in front of the negative 5, multiply negative 8 times the minus 5, that would be a plus 40. Copy the x over to the 1 less power. Negative 8 minus 1 would be negative 9. So h prime of x will be negative 36, x to the 5th, plus 40, x to the negative 9. Now we need h double prime of x. So h double prime of x will be this. Take the derivative over the first derivative. So if I do negative 5 times that negative 36, that would be a positive 180. Copy the x over to the 1 less power. It'd be negative 6. And then bring the 9 in front of the 40, negative 9 in front of the 40, so negative 9 times 40 would be minus 360. Copy the x over to the negative 10 power. That's the 1 less power. So h double prime of x will be 180 x to the negative 6 minus 360 x to the negative 10. And I believe that would be as far as I would go with this problem, because I don't think they want this using positive exponents. Okay. Let's try one more of these. We're going to find f double prime of x. Here, f of x is equal to, in this case, x squared plus 8, and that quantity is to the 5th power. Now this one we have to apply the chain rule, because at x squared plus 8 inside the parentheses, I can get the derivative of that. So, applying the chain rule, f prime of x would be this. We bring the exponent in front, copy over the x squared plus 8 in parentheses, that will be to the 1 less power. 5 minus 1 will be 4. And then we take the derivative on the inside of the parentheses. The derivative of x squared plus 8x will be 2x. Now, if we simplify this, 5 times 2x would be 10x times the quantity x squared plus 8, and that's raised to the 4th power. And now, do the second derivative, f double prime of x. Okay, so here's what f of x is. F prime of x is. We need to take its derivative by applying the product rule, because we got 10x times x squared plus 8 quantity raised to the 4th power. And the product rule is this. We take the first term, which is your 10x, times the derivative of the second. The derivative of the second, or the derivative of x squared plus 8, that quantity to the 4th would be there, so we bring the 4 down, copy over the x squared plus 8 to the 1 less power, and then take the inside derivative, which is 2x. So that represents the derivative of the second. And then plus the second, which is x squared plus 8, quantity raised to the 4th, times the derivative of the first. The derivative of 10x is just 10. All right, now let's simplify this. Let's try to clean all this up a bit. 10x times 4, that's 40x, times 2x will be 80x squared. 10 times 4 times 2, that's 80. X times x is x squared. Times the quantity x squared plus 8, and that's cubed. So now I'm going to put the 10 in front of the quantity of x squared plus 8 raised to the 4th power. Now let's do a little bit of factoring here. That 80 x squared and the 10, these two have a common factor of 10, so I can factor out the 10. I also can factor out x squared plus 8, but I have to factor out the one with the smallest exponent, and this one has the smallest exponent of 3. So that means x squared plus 8 quantity cubed can be factored out as well. Now, if I simplify this, take a look at this first term with what I'm factoring out. If I factor out a 10 from the 80x squared, I'm going to be left with 8x squared. And I've already factored out all of the x squared plus 8 quantity cube. That would be gone. Now compare that with the 10 times the quantity x squared plus 8 raised to the 4th power. 10 will be gone. 3 of the x squared plus 8 have been factored out. I'm left with only one of them, which is x squared plus 8. Now let's simplify what's inside that bracket. If I have 10 times the quantity x squared plus 8 cube, 8x squared plus x squared would be 9x squared plus 8. So this represents the second derivative of f of x. 10 times the quantity x squared plus 8 cube times 9x squared plus 8. And it's important that your algebra skills are in check. It's not the calculus that gets people, it's the algebra. And what I did here was just algebra right here from the second, third, and fourth lines down. That first line was just a calculus, applying the product rule. All right, so that's how we take second derivatives of functions. Now we're going to be using that to help us determine the intervals where the graph of a function is concave up or concave down. And here's the summary. For the intervals a comma b, if f double prime of x is greater than 0, then the function f of x is concave upward. And if f double prime of x is less than 0, then your function will be concave downward. And here's the summary of that. F double prime of x is positive f prime of x will be increasing, the graph will be concave upward. And these are just some examples of what concave upward looks like. Meaning if I draw a secant line, that means that secant line would be above the graph. F double prime of x is negative. That means that f prime of x will be decreasing. The graph would be concave down, and here's some examples of that. So if I draw a secant line, that secant line would be below the graph. Okay? Now let's look at some examples here. Let's look at an example. Let's say I want to find the intervals where the graph of f of x is equal to x cubed plus 24x squared plus 15x minus 12 is concave up or concave down. So, f of x is going to be x cubed plus 24x squared plus 15x minus 12. Now, of course, we have to find the first derivative and then find the second derivative to help us determine concavity. Okay, so the first derivative, f prime of x, is this. The derivative of x cubed will be 3x squared. The derivative of 24x squared will be a plus 48x, plus the derivative of 15x will be 15, and the derivative of minus 12 will be 0. So that's f prime of x. Now let's find f double prime of x by taking the derivative of the first, or the derivative of f prime of x. So in this case here, the derivative of 3x squared would be 6x, plus the derivative of 48x would be 48. All right, so that's our second derivative. Now what we need to do here is take that second derivative, f double prime of x, set that equal to 0. So here, f double prime of x was 6x plus 48, equaling to 0. And if we subtract 48 on both sides, you'll see that 6x is equal to negative 48. Divide both sides by 6, you're going to get x is equal to negative 8. Okay? Now, we're going to talk about what an possible inflection point is. But this x equals negative 8 represents a possible point of inflection because this may help us determine where the intervals where it's concave up or concave down. Here I'm drawing a chart like this one, and negative 8 is that point. Now, this number is going to separate the interval into two, the number line into two intervals. One will be from negative infinity up to negative 8. The other one will be from negative 8 to infinity. Okay. Let me make this 8 look like an 8. All right. Now here we're going to take a test value on each interval to determine whether it's increased, well, whether it's going to be concave up or concave down. Okay? Just like in this concavity summary up here. So, let's test a x value within this interval, like negative 9. Now, here we're going to substitute the x in f double prime of x with negative 9. So, f double prime of negative 9 would be 6 times negative 9 plus 48. 6 times the negative 9 would be negative 54. Negative 54 plus 48 would be negative 6. And here we got a negative value. So when f double prime of x is negative, that means that f prime of x will be decreasing. The graph will be concave downward. So here I'm just going to say that from negative infinity to negative 8, the graph of that function will be concave down. And now for negative 8 to infinity, that's this interval here, we're going to test, let's say x equals 0. And then use f prime of x and replace each x with 0. So this will be 6 times 0 plus 48. 6 times 0 is 0 plus 48 is 48. And 48 ended up is a positive number. So that means when f double prime of x is positive, that means f prime of x is increasing. The graph will be concave upward. Concave upward, or just concave up. All right, so let's go ahead and write down our intervals where it's concave up or concave down. Here it is concave up on the interval negative 8 to infinity, and concave down on the interval negative infinity to negative 8. Notice I'm using parentheses. All right, so if you notice, from negative infinity to negative 8 is concave down, and then from negative 8 to infinity is concave up. Notice that the concavity changed from concave down to concave up. That means this value of x, which is negative 8, we call that an inflection point. And that's the next thing we'll look at. We call that an inflection point. And it is the point on the graph where the concavity changes from upward to downward or from downward to upward. This means that if f double prime of x exists in a neighborhood of an inflection point, then it must change sign at that point. So the inflection point is usually going to be where your second derivative undergoes a change in sign, from positive to negative or from negative to positive. All right, so on the next page is a theorem that deals with inflection points. If the ordered pair C, comma, f of C is an inflection point of f, then C is a partition number for f double prime, or the second derivative. What that theorem means is that an inflection point can occur only at the critical value of f double prime. However, not every critical value produces an inflection point. All right? And of course, the critical value C for f double prime produces an inflection point for the graph of f only if f double prime changes sign at C, and C is in the domain of the function f. Okay, that's very important. And the procedure for testing inflection points will be this. Here's the procedure. You're going to find all the partition number C of f double prime such that f is continuous at C. And then step number 2 is, for each partition number called C, you're going to construct a sign chart of f double prime near x equals C. And then step number 3, if the sign chart of f double prime changes sign at C, then we can say that C comma f of C, that's the ordered pair, is an inflection point of f. If the sign chart of f double prime does not change sign at C, then there is no inflection point at x is equal to C. Okay. And at the bottom of this page, we're going to assume that f satisfies one of the conditions in the table below for all x in some interval a comma b, then the other conditions to the right of it also holds. Okay, this is just a summary of this here. If you have f prime of x being positive, that means the function is increasing. Or if f prime of x is less than 0, the function is decreasing. Or if f prime of x equals 0, that means your function is constant. We talked about that in the last video, section 4.1, dealing with first derivatives and their graphs. These last three, if f double prime of x is positive, that means that f prime of x will be increasing. Your function will be concave up. Or if f double prime of x is less than 0, that means that f prime of x is decreasing. Your function will be concave down. And if f double prime of x equals 0, that means that f prime of x will be constant. That means that the function f of x is linear. Okay. All right, let's look at this next example where we're going to find the x and y coordinates of all inflection points. The x and the y coordinates of all inflection points. Like in this case here, f of x is equal to 3x cubed plus 15x squared. F of x equals x cubed plus 15x squared. So let's find the first derivative here. Starting with f prime of x would be the derivative of x cubed is 3x squared, plus the derivative of 15x squared would be 30x. So to find the inflection points, we have to find out what that second derivative is. So the second derivative, f double prime of x, will be this. It will be 6x, plus the derivative of 30x will be 30. So that's f double prime of x. So to find our critical numbers, we're going to take f double prime of x and set that equal to 0. So that means 6x plus 30, which is what f double prime of x is, that's going to be equal to 0. And then we solve this equation for x. So if I subtract 30 on both sides, that means 6x is equal to negative 30. Divide both sides by 6, you're going to get x equals negative 5. So x equals negative 5 is what we call our critical number. It could be a possible point of inflection. We'll find that out to see where it's going to be concave up or concave down. So here, negative 5 is our critical number, and that's going to separate the number line into two intervals. One of them will be from negative infinity to negative 5. The other one will be from negative 5 to infinity. And then we're going to pick a test point for each interval. So like from negative infinity to negative 5, we're going to test some x value like, say, negative 6. And then replace the x in f double prime in our second derivative function with negative 6. So f double prime of negative 6 would be 6 times negative 6 plus 30. 6 times the negative 6 will be negative 36. Negative 36 plus 30 is negative 6. So here it's negative. That means from negative infinity to negative 5, that means our function would be, the graph of the function would be concave down. Concave down. And then from negative 5 to infinity, let's test 0, x equals 0. And then replace that 0 for x in the second derivative function. So f double prime of 0 will be 6 times 0 plus 30. 6 times 0 is 0, plus 30 is 30, and it is positive. That means from negative 5 to infinity, the graph of that function would be concave up. Okay. So as you can see here, there is a change in concavity from concave down on the left side of 5 to concave up of negative 5 to concave up on the right side of negative 5. So our point of inflection occurs at x is equal to negative 5, because we do have a change in concavity. So at negative 5, that would be our point of inflection. Now they want the x and the y coordinates of that point of inflection. So to find that out, we just substitute negative 5 in for x in the original function here, which is that f of x equal to x cubed plus 15x squared. So f of negative 5 would be this. X would be negative 5, and that's cubed, plus 15 times x, which is negative 5, and that's squared. Negative 5 cubed would be negative 5 times negative 5 times negative 5, or negative 125. Negative 5u squared would be 25 times the 15 in front would be 375. Negative 125 plus 375 will be 250. So the ordered pair, negative 5, 250, is our point of inflection. And that is what they were looking for. And of course, if you want to do that in the calculator, you can. X was negative 5, so that means I'm going to do left parentheses, negative 5, close parentheses, and then cube it, hack key and then cube, right arrow to get out of it, plus 15, then left parentheses, negative 5, close parentheses, hit the x squared button to square it. You'll see that you'll get the y coordinate of 250. Okay? So that's how we find our point of inflection. All right, this next example is also finding the x and the y coordinates of all points of inflection. This time we got f of x equal to 3 times x to the 9/5 plus 3. And here we want to find that point of inflection. So let's find the first derivative. That's f prime of x. And the way we're going to do that is this. I'm going to bring this 3 down. For x to the 9/5, I'm going to bring down the power, which is 9/5. Copy the x over to the 9/5 minus 1, because that's going to be to the 1 less power. That derivative of plus 3 is just going to be 0. So if I simplify this, this 3 is like 3 over 1 times 9/5. That will be 27/5. Bring the x down, and if you were to do 9/5 minus 1 whole, I'll do 9 divided by 5 in parentheses minus 1. Math key, select number 1. That'd be 4/5. So I have 27/5 times x to the 4/5 for the first derivative. Now I'm going to take that to find its second derivative, f double prime of x. So here again, I'm going to bring down the 27/5. For the derivative of x to the 4/5, I'm going to bring the power in front, copy the x over to the 4/5 minus 1. Because that's going to be to the 1 less power. Now, if I multiply 27/5 times 4/5, that would be 108 over 25. That's 27 times 4, that's 108. 5 times 5, that would be 25. Copy the x over to the 4/5 minus 1. I'll go and do that in the calculator as well. 4 divided by 5, close parentheses, minus 1. Hit your math key, select number 1 for the fraction. That'd be negative 1/5. So I have 108 over 25 times x to the negative 1/5. I can write that using positive exponents here, as the 108 would be in the numerator, the 25 would be in the denominator, and I'll bring that x to the negative 1/5 in the denominator as x to the positive 1/5. So that's f double prime of x. Now I'm going to take that f double prime of x, set that equal to 0, and try to solve for x. So here I have 108 over 25, x to the 1/5, equaling to 0. But I'm going to treat that 0 over 1. And if I try to do any cross multiplication, this one I'm going to have 108 times 1 would be 108. Then that's equal to 25x to the 1/5 times 0 is 0. And 108 equals to 0 is a false statement. Okay? However, we can find out the value of x where this second derivative is undefined. And in this case, by just looking at it, I can tell that 0 will have to be undefined, would be the value where the second derivative is undefined. Now, you can do this. Take that denominator of 25x to the 1/5, set that equal to 0, and solve for x. If you divide both sides by 25, you'll get x to the 1/5 equaling to 0, and then you'll have to raise both sides of the equation by the reciprocal of 1/5, which is 5. You'll see that x is equal to 0. So at x equals 0, f double prime of x is undefined at that value. So we'll use that as a critical number, okay? Critical numbers can be where x is equal to some number, or the value of x where our denominator is undefined. And x equals 0 was undefined because I would get a 0 in the denominator for the second derivative of that function. So let's use 0 there. All right, in this case here, we have two intervals. One would be from negative infinity up to 0, and then from 0 to infinity. Now let's pick test points for each interval. One test point for negative infinity to 0 will be just negative 1. And then we go ahead and substitute the negative 1 for the x in our f double prime of x function right here. So f double prime of negative 1 would be that 108 divided by 25 times negative 1 to the 1/5 power. And I will go ahead and use the calculator for this. Let's see, 108 divided by, and I'm going to put this in parentheses, 25, and then parentheses, negative 1, close parentheses, then the hat key to the 1 divided by 5, right arrow to get out of it, and then close parentheses. That came out to be like negative 4.32, which is negative. So that means from negative infinity to 0, the graph of the function will be concave down. And then from 0 to infinity, we're going to test, let's say x equal positive 1. So f double prime of positive 1 would be 108 divided by 25 times 1 to the 1/5 power. And I'm going to do this second and enter to copy this, and I'm going to delete that negative sign. Here's going to be positive 4.32. So that means from 0 to infinity, the graph of the function will be concave up. And notice we have a change in concavity. So that means at x equals 0, that will be our point of inflection. So the point of inflection occurs at x is equal to 0. But we do need the y-coordinate of that inflection point. So let's substitute 0 in for x in our original f of x function. So f of 0 will be 3 times 0 raised to the 9/5 plus 3. 0 to any non-zero power is 0. 3 times 0 is 0, plus the 3 there would be just 3. So we can say that our point of inflection will be the ordered pair 0, 3. So 0, 3 will be your point of inflection. All right. All right, now the next page, I think this is just a second derivative test, which is the kind of the summary of that, which is what we've been doing here for the second derivative test. Here, in this case here, f double prime of c, well, f prime of c is 0, but f double prime is constant. The graph would be concave up. We have a local minimum. For f prime of c, if it's 0, but f double prime of c is negative, that means it's concave down, meaning we have a local maximum. And then if f prime of c is 0 and f double prime of 0 is 0, then the test fails. And if the test fails, what you have to do there is use the first derivative test. And I would recommend going back to the video for section 4.1 to look at that first derivative test to see what's going on there. Okay. All right, so in example 7, excuse me, says here, find the intervals on which the graph of f is concave upward, the intervals on which the graph is concave downward, and the inflection points. So here we got f of x equals to 14, f of x equal to x to the 14 plus 8x squared. So first we find that first derivative, which is in this case here, the derivative of x to the 14 will be 14x to the 13th, plus the derivative of 8x squared would be 16x. And then if I take the second derivative of that, that'd be 13 times the 14, that would be 182. Copy the x over to the 1 less power, that'd be x to the 12th, plus the derivative of 16x would be 16. So f double prime of x will be 182x to the 12th plus 16. And then we're going to take that second derivative and set it equal to 0. So here we're going to have 182 x to the 12th plus 16 equal to 0. And let's see what we can do here. We can factor something out here. I believe I can factor out a 2 in this. If I did that, I will have 91 x to the 12th plus 8 equal to 0. And then we'll set each factor equal to 0. So this means I'll have 2 is equal to 0. 91 x to the 12th plus 8 is equal to 0. Now in this case here, that 2 is equal to 0, I can cross that out because that is a false statement. So that's gone. And I can try to solve 91x to the 12th plus 8 equal to 0 by subtracting 8. That will mean 91x to the 12th is equal to negative 8. If I divide both sides by 91, this one I'm going to have x to the 12th is equal to negative 8 over 91. And x is to an even power, as you can see. Which means this, there's no value of x where if I raise to the 12th power, I'm going to get a negative 8 over 91 from it. Okay? So, by looking at this, I'm going to say this. That x is to an even power. And is added to the second term. Okay? Because see, if you look at this, it's to an even power, where adding that to a second term is always going to be positive. So that means f double prime of x is always positive, no matter what x is. X can be negative, but it's to an even power. That's going to change it to a positive, and then you're going to add 16 to it. So that second derivative will always be positive. So that means that f of x is concave up. And it's going to be concave up everywhere from negative infinity to infinity. And because of that, the function itself has no inflection points. Has no inflection points. Okay. All right, here's another example of this, and I got a couple of examples of just concavity. Here we got f of x equal to x cubed minus 27x squared plus 2x plus 6. And I want to find the intervals in which the graph is concave up, the intervals in which the graph is concave downward, and the inflection points. And I'll go ahead and rewrite the function. F of x is equal to x cubed minus 27x squared plus 2x plus 6. And let's find the first derivative, f prime of x. The derivative of x cubed will be 3x squared. The derivative of minus 27x squared will be a minus 54x, plus the derivative of 2x will be 2, and the derivative of 6 will be just 0. So that's f prime of x, 3x squared minus 54x plus 2. Let's take that and find out what f double prime of x is. Bring the 2 down, multiplied by 3, it'll be 6x for the derivative of 3x squared, minus the derivative of 54x will be 54. And the derivative of 2 is 0. So f double prime of x will be 6x minus 54. Now let's take that second derivative, f prime of x, f double prime of x, set that equal to 0. So that means I have 6x minus 54 is equal to 0. And if I add 54 to both sides, you'll get 6x is equal to 54. Divide both sides by 6, you'll get x is equal to 9. So the critical number will be x is equal to 9. It could be a possible point of inflection. So at 9, we're going to have two intervals here on this number line. One would be from negative infinity up to 9. The second one would be from 9 all the way to infinity. And let's do a test value for each of those intervals. So for negative infinity to 9, I'm going to test x is equal to 0. And I'm going to use that f double prime of x to replace each x with 0. So f double prime of 0 is equal to 6 times 0 minus 54. 6 times 0 is 0. 0 minus 54 is negative 54. And it is negative, so that means from negative infinity to negative infinity to 9, the graph of that function will be concave down. And then from 9 to infinity, we're going to test, let's say x is equal to 10, and replace the x in the f double prime of x with 10. So it'll be f double prime of 10. That's equal to 6 times 10 minus 54. 6 times 10 will be 60. 60 minus 54 is 6. And it is positive. And if it's positive, that means from 9 to infinity, the graph of this function will be concave up. Here we got a change in concavity here. On the left of 9 is concave down, on the right of 9 is concave up. So that means that x equals 9, that will be our point of inflection. Okay, so let's go ahead and identify what's concave upward or concave up. From 9 to infinity, the graph of the function is concave up. From negative infinity to 9, the graph of the function is concave down. And now for our inflection point, the x-coordinate is 9, but we need the y-coordinate of that point of inflection. So that means we need to evaluate f of 9 by replacing each x in the original function with 9. So this will be 9 cubed minus 27 times 9 squared plus 2 times 9 plus 6. Now I'm going to do this in the calculator. Let's see, 9 hat key and then 3 for the cube, minus 27 in parentheses, 9, close parentheses, square it, plus 2, parentheses, 9, close parentheses, plus 6. I end up with negative 1434. So our point of inflection in this case would be the ordered pair 9, negative 1434. Okay? It's concave up from 9 to infinity. The interval where it's concave down is from negative infinity to 9. Okay? All right. Here's another one of these. Say we got f of x equal x to the negative 4 plus 20x cubed minus 20x plus 7. And we're finding the intervals on which the graph of the function is concave upward, the intervals on which the graph of the function is concave downward, and the inflection points. So in this case here, f of x is equal to negative x to the 4th plus 20x cubed minus 20x plus 7. And let's take the derivative of this function, the first derivative, by the way. The derivative of x to the negative x to the 4th would be negative 4x cubed. The derivative of 20x cubed would be a plus 60x squared, minus the derivative of 20x would be 20, and the derivative of 7 is 0. So f prime of x will be negative 4x cubed plus 60x squared minus 20. And let's find the second derivative, f double prime of x. The derivative of negative 4x cubed will be negative 12x squared, plus the derivative of 60x squared will be 120x, and the derivative of minus 20 will be 0. So f double prime of x will be negative 12x squared plus 120x. And now we're going to set f double prime of x to be equal to 0 to find out what our critical numbers are. So here I'm going to have negative 12x squared plus 120x. That's equal to 0. And I'm going to go ahead and factor out a negative 12x, because 12 and negative 12 and 20, negative 12 and 120 has a common factor of negative 12. And x squared and x has a common factor of x, so I'll factor that out as well. So if I do negative 12x squared divided by negative 12x, that's x. Positive 120x, positive 120x divided by negative 12x will be a minus 10 equal to 0. And then we're going to set each factor equal to 0. So that means negative 12x is equal to 0, and x minus 10 is equal to 0. Each equation we're going to solve for x. So for the negative 12x is equal to 0, that means x is equal to 0. And then for x minus 10 is equal to 0, adding 10 will give me x is equal to 10. So here I got two critical numbers. One is x is equal to 0. The other one will be x is equal to 10. Right? Now, let's check for their concavity. I'm going to say 0 is here. Say 10 is here. Now, I have three different intervals going on here. One of them would be from negative infinity to 0. The other one is from 0 to 10. And then the third one will be from 10 all the way out to infinity. Each interval, I'm going to select a test value. So for negative infinity to 0, I'm going to test, let's say, x equal negative 1. Now, using the second derivative function, I'm going to replace each x with negative 1. So f double prime of negative 1 will be negative 12 times negative 1 squared plus 120 times negative 1. That negative 1 we squared will be a positive 1 times the negative 12 will be negative 12. 120 times negative 1 will be minus 120. This will end up being negative 132, which is negative. So from negative infinity to 0, the graph of the function will be concave down. And then from 0 to 10, let's test an x value within that interval, like 1. Replacing the x in f double prime of x with 1, so that'd be f double prime of 1 equaling to negative 12 times 1 squared plus 120 times 1. 1 squared will be 1 times the negative 12 in front will be negative 12. 120 times 1 will be 120. Negative 12 plus 120 will be 108. And it is positive. So that means from 0 to 10, the graph of that function would be concave up. So I do see a change in concavity at 0. Now, what about for 10 to infinity? Let's see if there's a change in concavity at 10. Let's test, let's say x is equal to 11, and then do f double prime of 11. That'd be negative 12 times 11 squared plus 120 times 11. And I'm going to put this in the calculator. So here this will be negative 12 times 11, close parentheses, squared, plus 120, open parentheses, 11, close parentheses. This ends up being negative 132. And it is negative. So that means from 10 to infinity, the graph of the function will be concave down. So we do have a change in concavity at x equals 0 because to the left of it is concave down, to the right of it is concave up. Also, we have a inflection point at x equals 10 because there's a change in concavity as well. To the left of 10, the graph is concave up. To the right of 10 is concave down. So we're going to identify what's concave up. It's concave up on the interval 0 to 10, and it's concave down on two intervals, from negative infinity to 0 and from 10 to infinity. And this time we have two inflection points, one at 0 and the other one is at 10. So our inflection points occur at x equals 0 and at x is equal to 10. Now we need to find out what the y values are for each of those x values, because the inflection point is an ordered pair. All right, let's start with x equals 0. We're going to substitute each x in the original function with 0. And I think 0 is going to be quite easy to do because you can have negative 0 to the fourth plus 20 times 0 cubed minus 20 times 0 plus 7. And I can tell you right now, this will be 0, this will be 0, that will be 0. Plus 7 ends up being 7. So 0, 7 is one point of inflection. Now for x equals 10. Use the original function, replace each x with 10, so I got negative on the outside, that'd be 10 to the fourth, plus 20 times 10 to the third, minus 20 times 10, plus 7. And I'm going to need a calculator to do this one. Got the negative, just say 10 hat key 4, plus 20, left parentheses, 10, close parentheses, hat key for the 3, 20, left parentheses, 10, plus 7. I end up with 9,807. So the other point of inflection would be 10 and 9,807. These two right here are what we call points of inflection. Those are points of inflection. So here we got two of them. All right. And finally, example 10. This is an application problem dealing with the second derivative in their graphs. The marketing research department of a computer company used a large city to test market the firm's new laptop. The department found the relationship between price, which is P, dollars per unit, and the demand, X, units per week, was given approximately by the following equation. P is equal to 2,646 minus 0.18x squared, and that is when X, the number of units per week, is between 0 and 100. So weekly revenue can be approximated by the following equation. R of X is equal to X times P, which is equal to 2,646x minus 0.18x cubed, and that's where X is between 0 and 100. Here we're going to use this information to find parts A and B. And in part A, you're going to find the local extrema for the revenue function. What is or what are the local maximum or maxima, and then you'll select the correct choice below, and if necessary, fill in the answer box to complete your choice. And then you're going to find the local minimum or minima. Do the same thing. And then part B would be, on which intervals is the graph of the revenue function concave upward or concave downward? So we're going to answer each part one at a time. Starting with part A is finding the local extrema for the revenue function. That's, of course, the local maximum and the local minimum. And I need to do this on a separate sheet of paper here. So in part A, we have the function R of X equaling to 2,646 minus 0.18 x squared. Oh, I'm sorry. R of X. I was copying down the price function. Okay, I left out the X here, so it'd be 2,646x minus 0.18 x cubed. Okay, here they want the weekly revenue. Okay, and we're dealing with the revenue function here, by the way, in part A. All right, so first of all, we need to, when we're finding the local maximum and local minimum, we need to take the first derivative. So R prime of X is this. The derivative of 2,646x would just be 2,646 minus the derivative of 0.18x cubed would be 0.54. You bring the exponent down, multiply by 0.18, you'll get 0.54. Copy the x down to the one less power. That's your first derivative. Now we're going to set R prime of X equal to 0 to find out what our local maximum and local minimum is going to be. So let's take 2,646 minus 0.54 x squared and set that equal to 0. And what I'm going to do is move that minus 0.54 x squared over to the other side. I'm going to get 2,646 is equal to 0.54 x squared. And then to get x squared by itself, I'll divide both sides by 0.54. That would mean x squared is equal to actually 4,900. And of course, you can verify that by doing 2646 divided by 0.54. You'll see it's 4,900. And then to solve for x squared, or to solve for x is squaring it. I'm squaring it, so I need the square root on both sides, and I do need to include the plus or minus symbol when I do that. So that means x is equal to plus or minus the square root of 4,900. That's 70. And what that means here is this, that x is equal to 70 or x is equal to negative 70. And keep in mind that we are dealing with, in this case here, units of a computer, and that can't be negative. So we need to eliminate the negative part and only deal with the positive value. So that means x equals 70 would be our critical number. All right, so let's go ahead and find where it's increasing or decreasing and find out whether we have a local maximum or a local minimum. Let's see, 70 is going to be here. And I do have two intervals here. And let me tell you this, my restriction here in this problem is from 0 to 100. Here it is, 0 to 100. So that means 0 has to be here and 100 has to be here. So the interval will be from 0 to 70, and the other one will be from 70 to 100. Okay? Now let's pick test values here. Between 0 and 70, I'll pick a test value, let's say 10. And place the x with 10 in this first derivative function here. So r prime of 10 would be equal to 2,646 minus 0.54 times 10 squared. And for the sake of time, I'll just do this in the calculator. 2,646 minus 0.54 times 10 squared would be 2,592. And it is positive. So that means if it's positive, that means from 0 to 70, the graph of that revenue function will be increasing. And for 70 to 100, let's pick 80 as a test value. The x and the r in that first derivative function with 80. So r prime of 80 would be 2,646 minus 0.54 times 80, and that's squared. Now do this in the calculator as well. 2,646 minus 0.54 times 80, and that's squared. Here I get a negative value of negative 810. And it is negative. So that means on the interval from 70 to 100, our revenue is decreasing. So we have a change here from increasing to decreasing. Let's take a look at that. Increasing up to 70, and then after 70, it decreases. So that tells me at 70, there is a local maximum, okay? A local maximum. that x is equal to 70. Okay, so let's see if we can answer part A. It says that the local maximum is or are at x is equal to, there is one, and that's at x equals 70. In this problem, there is no local minimum, so for that part, we just check off or select the one that says there is no local minimum. So that represents part A. Now, part B says here, we want to find out where the graph of the revenue function is concave up. Find those intervals and the ones where it's concave down, okay? So now, this is part B. We have our first derivative, and I'll go ahead and rewrite that as r prime of x equaling to 2,646 minus 0.54 x squared. Let's find the second derivative, r prime of x. Well, the derivative of 2,646 is 0. The derivative of negative 0.54 x squared would be a negative 1.08 x. Bring the 2 down, multiply by the negative 0.54, you'll get negative 1.08. Copy the x down to the 1 less power. So r double prime of x would be negative 1.08 x. Take that second derivative, r double prime of x, and set that equal to 0. So negative 1.08 x equals 0. Divide by negative 1.08 on both sides, you'll get x is equal to 0. So that's a critical number. All right, so now let's do a sign chart to find where it's concave up or concave down. Oops. Zero is here. So the intervals would be dealing with would be from negative infinity to 0. The other one would be from 0 to infinity. All right. For each interval, we'll do a test value. Use the test value. So let's test from negative infinity to 0, let's say negative 1. And substitute the x with negative 1 in the second derivative function. So r double prime of negative 1 would be negative 1.08 times negative 1. That would be a positive 1.08, which is positive, as I mentioned. So that means for our second derivative, the graph of the function is concave up. Second derivative is positive, that means it's concave up. From 0 to infinity, let's test positive 1 as an x value. And then replace the x with the 1 in the second derivative function. So it'd be negative 1.08 times 1, which is, of course, negative 1.08. And it is negative. That means the graph of that function would be concave down, since our second derivative came out to be negative. And at x equals 0, we know there's a point of inflection because of the change in concavity. Okay? And they do want the interval notation for this one. So the graph is concave up from negative infinity to 0, and the graph of the revenue function is concave down 0 to infinity. So going back to that problem, we say that the graph is concave up. Check that off. From negative infinity to 0. And the graph is concave down. We select that from 0 to infinity. and they want the answer in interval notation. Okay. All right, so that's how we solve this particular problem. All right, so that does conclude this video on section 4.2, dealing with second derivatives and graphs. Feel free to reach out to me if you have any questions about any of the problems that were presented in this video or any of the problems that are in my math lab.